Hello students. So today we are going to start the unit second, that is your Laplace transformation and Laplace transform. And before this you have till now your completed unit 1, that was related to your differential equation. So in order to start this unit that is related to your Laplace transformation and Laplace transform, we must first we will try to understand what is your transformation and transform is, so that we can then correlate the things with Laplace transformation. So you know very well that we have your differentiation or the concept of derivatives. So what we do in your differentiation, so in differentiation, like you know very well, just we have a function and we take its derivative. We function have, say you have function fx and you take its derivative and you get derivative f dash x. This is your differentiation in general, if we say. So if I represent this operator dy dx by capital D, then I can write this differentiation derivative as your this one. Okay, so you know very well, this is something like if you have say sin x, then this is basically d by dx of sin x, and then you are getting cos x. So what is happening here in the differentiation, you are applying some operation on function fx, and that operation you call it as differentiation. And when it is applied on function fx, then after applying it you get its derivative. So this derivative is something you apply it on sin x, you got its derivative cos x. So here the operation of differentiation that we are using here is a transformation and on applying this operation, the function you are getting, that is its derivative, it is your transform. So basically transformation is nothing, it is basically an operation which when applied to some function fx changes the given function into another function, that we call it as transform. Here in differentiation is a transformation, because whenever you differentiate a function you get its another function derivative, and that is your transform. So this is what a transformation is. Transformation is a operation, transform is the resultant product that you get after applying that operation. Similarly, the same concept is for integration, that we know very well that if I say represent the operation of integration by capital I and I apply it on fx some function, then I got its integral. I will get its integral. So something like you integrate function cos x and you get sin x plus no doubt constant of integration. So this is what we do in integration. So the operation of integration is a transformation. And after applying the operation of integration, whatever you get is your transform. So this is what your transformation and transform is. So similar concept now we will apply to Laplace transformation and Laplace transform. So continuing this, that what now we have your Laplace transformation and Laplace transform. So from the above, one thing is clear, transformation is your operation and transform is the function that you obtain after applying that transformation. So Laplace transformation and Laplace transform. So what its actual definition of this Laplace transformation and Laplace transform. So let me write it here. The Laplace transform or Laplace transformation denoted by capital L. It will usually be denoted by capital L, as in case of differentiation you represent it by operator D. In case of integration you represent it by capital I. Similarly in Laplace you represent it by capital L. Laplace transformation of a function fx is given by Laplace. You are applying operation on function fx. We call it Laplace transform, and this operation is of this form: e raised to power minus px fx dx. And on applying this operation you get some function in terms of parameter p, where p is a parameter, a real number. So here this capital L is your Laplace transformation. This is Laplace transformation. Capital L is representing a transformation that we call as Laplace transformation, and it is an operation. It is operation which when applied on fx, and this operation is of this form, that it will be acting on some function in this way: 0 to infinity e raised to power minus px fx dot dx. And whatever you get after solving this integral, provided this integral exists, you get fp, and this is your Laplace transform. After applying the transformation, whatever you get in terms of your p, a parameter, a real number, we call it as Laplace transform. So here is what the Laplace transformation and Laplace transform is. So basically again it is an operation, and transformation is an operation, and transform is the product that we get after applying that transformation or Laplace transformation. Okay, so now what is the use of this Laplace transformation? That what are the main reasons that we are studying this Laplace transformation? So significance of your Laplace transformation, I am representing it by short form LT. Now in brief I will be taking one of few cases where we will see the significance of Laplace transformation or Laplace transform. So it is basically used to solve the differential equations. Remember that in case of your differential equation we did in the last unit, we solve the differential equation, non-homogeneous differential equation, using the first we find the general solution of homogeneous differential equation, then we find the particular solution of non-homogeneous differential equation, then we add those, and finally then under given condition we find the particular solution. So that is a long way. Also the method that we have done for solving the differential equation in unit 1, that were very lengthy or were restricted to certain type of functions or under certain conditions. However, in Laplace transform we are not going in that long way or in that your complicated ways. It is very simple to operate or solve the initial value problem, boundary value problem using Laplace transform. And especially its importance comes into picture when you have, say you have a, let us, since we have done mostly your second order partial differential equation, say you have this type of second order non-homogeneous differential equation. So if in such type of non-homogeneous differential equation, if Rx is in complicated form, is a very complicated function, or functions like unit step function, in the form of unit step function, then actual power or importance of Laplace transforms comes into play. There we will see that how easily Laplace transformation help us to solve such type of differential equation when Rx in such type of differential equation is in the terms of unit step functions or some complicated functions. And finally, not least, it can be used to solve integrals like sin x upon x that are not solvable using the exact techniques. So we can also solve these type of integrals using your Laplace transformation. We will see this later. So this is the things that we use to solve the why we use Laplace transformation. So these are one of the few things that we will be doing in this chapter. Here we will see how we can use Laplace transformation to solve the differential equation and integrals like this one. Now, before going further, there are few terms that must be clear to us for understanding the concept of Laplace transform. So the thing is that when we will be doing certain formulas and other things, then we will be using certain terms. So one of the few of the certain terms that we will be using frequently are, first is your piecewise continuous function. Another is exponential order, because in this most of the unit we will be doing the formulas, and in that formulas we will be frequently using these terms: piecewise continuous function, exponential order. So we must be very much clear about these terms, that why we are using these terms and what are these. So let us start with your piecewise continuous function. What is your continuous function? We know very well, but what is your piecewise continuous function? So a function fx is said to be, let me write the definition, is said to be piecewise continuous, function on finite interval a less than x less than b, say, where f is defined, if this interval can be divided into finite number of subintervals, such that in each subinterval fx is continuous, except possibly at finite number of points where fx has jump discontinuities. So what a function is, when a function is said to be piecewise continuous on some finite interval, we say that it is piecewise continuous on some finite interval if this interval can be divided into finite number of subintervals, such that in each of the subinterval fx is continuous. That is okay, except possibly at finite number of points where fx has jump discontinuity. That is, we will say that a function is a piecewise continuous even if at some of its finite points it has jump discontinuity. So what is jump discontinuity? It means the limit of function from right and left, that is its left hand limit and right hand limit, exist but they are not equal. So we will be getting these type of discontinuities under such type of piecewise continuous function. So in piecewise continuous function, such type of discontinuities are there, jump discontinuities are there, where you have the left hand limit, right hand limit, both exist but they are not equal. For an example, let me consider one of the best example to show that a function is a piecewise continuous function. So you consider here unit step function and say x is taken to be greater than or equals to 0. So it is 1, here it is 2, here it is 3, say 1, 2, 3. So you know this is your, here it is this one, then this one, and then you have this one. So like this is your unit step function, and here you can see at every of the step point 1, 2 or 3 you have the limit approaching from your left and approaching from right. They both exist but they are not equal. You have a jump here in each of these points 1, 2 and 3. You have a jump here, you have a jump here. So clearly you can see here, that these type of inequalities, discontinuities, jump discontinuity, the both limit from left and right exist. But the value at the given point, both limits exist from left and right hand side, but they are not equal. So this is one of the example where you can see that what the piecewise continuous function is. Second example I can show you by a simple graph. Say this is A, this is B. So let me take this point as A1, and here it is, say like this, and then you have say like point B1, and this is going like this one. Yes, here it is. So clearly you can see this function is a piecewise continuous function. You can see discontinuities, jump discontinuities at A1 and B1. From left hand side, if you approach, you will be getting some value, and from right hand side, if you approach, you will get some other value. Although limits exist from left and right, but the value is your different. Similarly, for the case B1, you can see there is a jump. If you go from left this side or from right side, the values are different although the limit exists. So these type of functions are considered under piecewise continuous function, that they are continuous but in some of the points, finite number of points, they have jump discontinuities. Limit exists from both sides but they are not equal. So we can also now take some of the examples related to your piecewise continuous. So let us, if you understand the concept, check whether function fx equals to cos x upon x is piecewise continuous for all x greater than or equals to 0. So we have to check whether this function fx is piecewise continuous for all x greater than or equals to 0. So now here in such type of function we will be looking at the points where the limit of the function do not exist when we approach from left or right. So clearly in this function we can see if we approach the function fx from, we approach function at point 0 through right hand side, then clearly you can see this is your cos 0, that is 1 upon 0, that is 1 upon 0, and that is infinity. So clearly you can see you are getting this value limit at point 0 when we approach from right hand side, limit is getting infinity. So limit does not exist here. So here right hand limit does not exist at x equals to 0, since we can take only right hand side, since we have x greater than or equals to 0, and that too does not exist at x equals to 0. We do not have any other problem at any of the other point, but at x equals to 0, since it is considered in the question, right hand limit does not exist, so fx is not continuous, sorry, not piecewise continuous, is not piecewise continuous for all x greater than equals to 0. So this is how we can check the function whether it is, because here you have a infinite discontinuity, the limit does not exist here, you have a infinite discontinuity at point 0. So this is your first example, that how to check your piecewise continuity. Now let me take another example for piecewise continuous function. Say you have example this one, x less than 0, x here, 0 less than x less than 5, and 7 when x is greater than equals to 5. So clearly in this case, if I plot it, then its graph will be 1, 2, 3, 4, 5, 1, 2, 3, 4. So for this is, say this is 4, I am just not taking it on scale, and this is 7. So x plus 4 is the straight line, this one, and this is your whole, this is first x plus 4. Then you have x here from 0 less than x less than 5, so this is 5, this is minus 4. So y equals to x here, so at x equals to 0 it is 0, and then it is going up to x here till 5. So 5, if it is, say, let me take 7 here and 25 here, because it is x here, so at 5 it will be 25. So let me just, without any scale, let me take it to 25. So this is y equals to x square, y equals to x square for 0 to 5. So this will be curved like this, and then for x greater than equals to 5 it is 7. The 7 is somewhere here, so it goes like this one. So clearly you can see now, it is a piecewise continuous function. You take any of the limit x tending to, even from the graph it is crystal clear that function has a jump discontinuities. At x equals to 0 you have a jump discontinuity, but the limit, yes, limit from right hand side and left hand side both exist, but they are not equal. As you can see, if you approach 0 from left hand side, then it is your x plus 4, and that is your 4. And if you approach 0 from right hand side, then you have this equals to 0. So clearly limit both exist, but they are not equal, so you have a jump discontinuity here, and function is piecewise continuous. Similarly, for x equals to 5, you can see you have a jump from here to here about point x when you approach from left and right hand side. So this function is your piecewise continuous function, as you have jump discontinuities at x equals to 0 and x equals to 5. Now say in the same question, if I replace this 1 upon x square y, say 1 by x, the same question, say if I replace 1 by x y 1 upon x square, sorry, so x square y 1 by x, then the graph is going to be like this one. Say if it is 5, at the value 5 you have 1 upon 5, 0.2, say here it is 0.2, so I am just going it like this one, this is. So now if same function, I just make some modification in its middle part, 0 to 5, you can see now at x equals to 5 you do not have any problem, at x equals to 5 you do not have any problem, but because, let me just write it, this is your whole, not the original value, this is whole. So at x equals to 5 you do not have any problem, because when you are approaching from left you are getting value 0.2, and from right when you are approaching you are getting value 7. So both limit exist and are defined. However, when we are talking about x equals to 0, you have function limit x tending to 0 positive when you approach this function from right hand side, because you have x greater than 0. You have this function when x is greater than 0. Then this is infinity. This is infinity. You have infinite discontinuity. Limit does not exist. Limit does not exist in this case when you approach this 0 from right hand side. Limit does not exist. So now you, in this case, in this function have no jump discontinuity at x equals 0, but infinite discontinuity at x equals 0 when you approach from right hand side. So this is not piecewise continuous. So this is how we show that a given function is piecewise continuous or not. So that's only two things we have to remember. Limits about any point should exist and they should not be equal. If they are not defined, the limit from any of the side left or right is not defined, does not exist, then it is not going to be piecewise continuous. Second term that we were using here, we will be using, is exponential order. Is your exponential order. So what is your exponential order? This is a function fx is said to be of exponential order c if there exists constant m, if there exists constant m greater than 0 and a real number x 1, such that mod fx is less than equals to m dot e raised to power cx for all x greater than x1. So this is the definition of the function which is said to, when it is said to be exponential order. So we say function is of exponential order c if we got some constant m, positive constant, and a real number x such that the modulus of fx is less than equals to m times e raised to power cx. Geometrically it means that the growth of function fx, is less than or equals to constant times the growth of exponential function. So how now to check that whether a given function is exponential order or not? So let me take an example. Check whether the function fx equals to sin x is of exponential order or not. So this is a question that we have to now solve. Check whether given function is of exponential order or not. So we will be using here method 1. There are two methods to check these type of check exponential order, that whether function is of exponential order or not. So we are using method 1 where we directly use the definition. Here is your definition. So we use this definition as such where it can be applicable. For an example, here you have fx equals to sin x. You have fx equals to sin x. So I am taking the mod of this fx, and this is equals to sin x, and this is less than equals to 1. Now by the definition of exponential order, fx is less than equals to m dot e raised to power cx. Then I call, if I am getting this type of relation, I will call fx of exponential function of order c. So now I can write this 1 as 1 dot e raised to power not x. So comparing 1 with 2, or let me write it more properly, mod fx is less than equals to 1 dot e raised to power not x. So clearly m is equals to 1, c equals to 0. Comparing this with equation number 2, the standard definition, we get c0. So fx equals to sin x, fx equals to sin x is an exponential function of order 0. So this is how we can use definition as such to find whether function is exponential order or not. Now let us use method 2. Sometimes because method 1 does not work, so we have to change our strategy there. So here it is your example 2. So before taking example 2, let me discuss in brief what is method 2. Since function is, if it is of exponential order, then we have something like this, where m is greater than 0 and x is greater than x1. So we got something like this. So what we do whenever we are not getting the answer or in this form, a function in this form, what we do, we take this e cx this side, and we got e raised to minus cx mod fx less than equals to m. That is, we try to show that this quantity, this term, is bounded above by some finite positive constant m. So that is now the second method, where we, instead of taking the mod of fx, we consider this term and try to see whether it is bounded above or not. So that is our second method. So let us check, apply this for function fx equals to cos x. If fx is this one, check whether it is of exponential order or not for all x greater than equals to 0. Whether it is of exponential order for all x greater than equals to 0 or not. So let us say if I just start with mod fx that we did in the early case also. So it will be this thing, mod cos x upon mod x less than equals to 1 upon mod x, where x is greater than equals to 0. So clearly you can see from here we are not getting any idea that to show that a function is of exponential order or not. So let us try to, because from here we can't say anything about the exponential order, because for x belonging to 0 1 we do not have anything. X belonging to 0 to 1 we can't say anything regarding exponential order. So let me take the route 2, the method 2, where I must now check this thing, that is mod cos x upon x, and that now comes out to be e raised to power minus cx upon mod x. So I got this thing. Now from here we can see limit as x tending to 0, because he is asking the question for all x greater than equals to 0. So although for all other x we can say something, but for x tending to 0, because there we have a problem, x tending to 0, you have this e raised to power minus 6x upon mod x that tends to infinity. See, positive or negative, you can take any, and you will see for x tending to 0, 0 positive if you want to add, this limit is going to be infinite, that is not bounded. You can't bound this value, when you approach x from right hand side. That is e raised to power minus 6x mod fx that you have got equals to this thing mod x is not less than equals to m for all x greater than equals to 0, because at x equals to 0 or as x approaching to 0, this value of this function is tending to infinity. You can't bound this value as you approach near to 0 from right hand side. So this is not bounded function as you approach to 0. So it implies fx is equals to cos x upon x is not a piecewise continuous function. Is not a sorry exponential order is not of exponential order for all x greater than equals to 0. You have a problem for x lying between 0 and 1 including 0. Now, so this completes whatever has been asked in the question, but let me add one more thing. Since we in the method before starting this we have this thing, and you have mod cos x upon this, and this comes out to less than 1 by mod x. Now for all x he is asking for all x greater than equals to 0. So you have a problem between this interval. So if say this is less than, you got mod fx less than equals to 1 upon mod x, and this is always less than equals to 1 for all x greater than equals to 1. So if I exclude the interval closed 0 to 1 open this interval, then I have this mod x less than equals to 1. I am getting then bounded function, that is this mod fx is less than equals to 1, that is 1 dot e raised to power naught x for all x greater than equals to 1. So in that case f is the function given is of exponential order 0 for all x greater than equals to 1. So the given function now is of exponential order 0 for all x greater than equals to 1. However, if we are considering the x from 0, then that is not possible, because at 0 the function is not bounded. So this is in addition to the given question that yes, this function is piecewise continuous for all x greater than equals to 1, but not for x greater than equals to 0, because you have a problem in interval closed 0 to open 1. Okay, so these were the few terms that we will be frequently using while we will be doing various formulas for Laplace transformation or Laplace transform. So now let me define the existence theorem, under which we define these two terms of piecewise continuity and exponential order. Existence theorem for Laplace transform. So this theorem will tell you that when the Laplace transform of given function will surely exist, and these two conditions of piecewise continuity and of exponential order, they make sure that the Laplace transform of the function exists. Okay, so remember, we write the Laplace of function fx as 0 to infinity e raised to power minus px fx dx, and this is equals to f, and we usually write that provided this integral exists, that this integral exists or not. So what the existence theorem says, it says that if fx is defined and piecewise continuous on 0 to infinity or x greater than equals to 0, this is 0 to infinity, just let me, yes, here it is, 0 to infinity for x greater than equals to 0, and is of exponential order c, that is mod fx is less than equals to m e raised to power cx for all x greater than equals to 0, then we say Laplace transform, and we say Laplace transform of fx, that is this one, Laplace transformation or Laplace transform of fx will always exist for p greater than c. So these are the two conditions of piecewise continuity. Now our function is to be defined on the given interval or x greater than equals to 0, and it is of exponential order c for all x greater than equals to 0. Then he says the Laplace transform of the given function, this integral, will always be going to exist. Then the Laplace of the function will exist, that is, this integral will exist for p greater than c. That this condition p greater than c comes from the fact that we will see later that how this p greater than c, while we will be working for formulas, we will see how this p greater than c comes, and c is basically the exponential order the function has. So these two conditions of piecewise continuity and exponential order, no doubt function is to be defined. If these are there for x greater than equals to 0, then the Laplace of given function is going to exist always for p greater than c. Now, before moving forward, one more thing, condition of your piecewise continuity, and of exponential order is sufficient condition for the existence of Laplace transform. What does it mean? It means that if you have a function which is not piecewise continuous and even not exponential order, or even if it is not piecewise continuous, any of the two conditions fail in some function, even then the Laplace transform of that function can exist. Even if the both conditions are not there in case of some function, even then the function Laplace transform can exist. So this condition is sufficient. Sufficient means that when these two conditions are fulfilled, then it is always sure that Laplace will exist. It is going to be there. Laplace is going to exist if these two conditions for any function hold. However, if any one of the conditions fail, whether it is of piecewise continuity or of exponential order, or even both conditions fail in some function, still the function can have Laplace transform. So this condition is not necessary. These conditions are not necessary. They are sufficient. Okay, sufficient means that if they are there, then Laplace is going to exist. However, if they are not there, still Laplace can exist. Now, finally, one more thing that I need to add here. Yes, here it is. If Laplace of fx exists, that is, say you find the Laplace of some function and you got fp. If it is existing, then the fp you will get always will tend to 0 as p tends to infinity. So this is one of the important relation, that whenever you are finding the Laplace transform of a given function, so whatever Laplace transform you will get, that will always tend to 0 as p tends to infinity. So you will never get cos p, sin p, ln p, e raised to power p, the Laplace transform of any function. You will not be getting that if you apply Laplace transform of apply Laplace transformation on some function and you get the Laplace transform in this form. Why? Because they are not tending to 0 as p tends to infinity. So whenever Laplace exists, the Laplace transform always tends to 0 as p tends to infinity. So this is about your introduction about the Laplace transformation, Laplace transform, and its existence, in which we discuss the properties of your exponential order and piecewise continuity. And in the next lecture, we will discuss the various formulas that how to find the Laplace transforms of various functions. Thank you. Thanks a lot.